So we've talked about how to identify a true outlier using the 1.5 IQR rule. We talked about how to make a box plot. Now we're going to actually do it with some examples. Here's the data on the number of goals scored in 16 games played by the 2016 U.S. women's soccer team. The data has been put in order for you from least to greatest. Don't get used to that. It's not always going to be that way. But we need to calculate the 5-number summary and the IQR. Remind me again, what 5 numbers are in the 5-number summary? Minimum, Q1, median, Q3, maximum. Perfect. Obviously, the minimum's super easy. What is the minimum? 1. Maximum's really easy. What's the maximum? 13. Okay, cool. Let's go find the median. High, low, do, 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 do. Okay, I've got 2 numbers in the middle. So what do? I average them. What is the average of 2 and 3? 2.5. So basically my median is right here at 2.5. There's my median. Now we're going to find the median of the lower half of the data. That's going to be Q1. So find the median of the lower half of the data. And what you get? Right here. Yep. So it'll be 1.5. And then we're going to find the median of the upper half of the data. And that would be right here. So what's the median of the upper half? 5. Very good. And now we're going to find the IQR. Oh my gosh, I'm getting so old, you guys, I forgot. How do you find IQR again? Q3 minus Q1. Nice. All right, so 5 minus 1.5. What is 5 minus 1.5? 3.5. So my IQR is 3.5. The distance between Q3 and Q1 is 3.5. Anybody have any questions on finding the 5-number summary and the IQR? Feeling good about that? Okay, let's see if there's any true outliers then. We're going to do 1.5 times that IQR number. 1.5 times 3.5. What is 1.5 times 3.5? 5.25. Nice. So we're going to take Q1 and we're going to subtract that 1.5 IQR number. So Q1 was 1.5. And we're going to subtract 5.25. Now, sometimes this is going to happen. You're going to get a negative number. That just means obviously you have no lower outliers because you don't even have negative numbers in your data. But this is negative 3.75. Is that right? Yes. Okay. There's no lower outliers. There's no value that is lower than negative 3.5. So now we'll check to see if there's any upper outliers. We're going to take Q3 and add the 1.5 IQR number. So that would be 5 plus 5.25. A little easier math here. What is 5 plus 5.25? 10.25. Is there any number in our data that is bigger than 10.25? Yep, what is it? 13 is an upper outlier. 13 is an upper outlier. So now we just need to make this box plot. First thing you do is you make a number line that goes from the lowest to the highest number. This is number of goals. Now for when you're making a box plot, you're going to want to make the inner or the box itself, the IQR basically, you're going to want to make that first. And so for this one, our Q1 was at 1.5. Our median was at 2.5 and our Q3 was at 5, and there's our box. So we have our box. We're going to go now from our Q1, we're going to go to the lowest non-outlier value, which happens to be the same as our minimum of 1. So that's our low whisker. And now, when you are making your whisker, you don't go to the outlier. You go to the highest or lowest non-outlier value. So what's the highest number in our data that is not an outlier? 10. So we'll go to 10 and stop the whisker. And then we'll put a star at 13 to show that there is an outlier there. And that's how you make a box plot. Do you guys have any questions? All right. I did this one. You do the next one. You got it. I have faith in you. All right. Hopefully this was your 5-number summary when you did this. Hopefully you got 1, 2, 4, 6, 7, 6, 6, and 11. So we got? 5. Just kidding. 5 and 11. There you go. 1, 2, 4, 5, 11. And then your IQR should have been 5 minus 2, which was 3. Everybody got all that? Perfect. Outliers, what'd you find? 11 is an upper outlier. What else? Anything else? Any lower outliers? No. 11 is definitely an upper outlier. Very good, very good. And then you have been asked to make parallel box plots for the men versus the women. So what does that mean? That just basically means they're going to share an x-axis. They're going to share the x-axis. And so here's our parallel box plots. When you make parallel box plots, make sure you label which one is which. It doesn't matter which one's on top. Just make sure you label which one you put where. But again, parallel anything, parallel box plots, parallel dot plots, parallel histograms, just means that they share an x-axis. And so here they are. And that makes it easy to compare. So somebody tell me, give me a comparison statement between these two box plots. Yeah, the minimum for both is 1. Good. Yes, sir?
The median for men is higher, but women have a higher maximum score.
Perfect. The median for men is higher than women, but the women have a higher maximum score. Perfect. One more. Give me one more. Anyone? Ah, yes. Quartile 3 is at 5 for both. Quartile 3 is at 5 for both. Very good. What questions do you guys have about box plots? Identifying outliers? So fun. What about shape? Oh my gosh, shape. The shape of box plots can sometimes be tricky, so I'm going to show you guys a little trick so that you can avoid the trickiness. For box plots, That middle line in the box is the median, which the median is pretty close to the peak in any distribution. It's not exactly the peak, that's the mode, but the median's pretty close to the peak. So if I think about the median being close enough to the peak, and then I just draw a line down to each side, boom, what shape is that?
That's a foot. A foot.
You think you need to see the foot? You need to see the toes on it? Okay.
With the toenails.
Why is it a triangle?
All right. What foot is that? That's a left foot. So this is left skew. You got it. Nice. All right, so let's look at the test grades on the right here. On the top, class number 1. So again, think about the peak being close to the median or whatever, and then go down to both sides. What do you think? It's definitely, well, yes, maybe. What do you think? This one's fairly symmetric. That one's pretty symmetric. How about class 2? Class 2, what do you think? This one has a slight left skew. This is probably a slight left skew. It's just a little skewed. I honestly, if you told me that one was approximately symmetric, I probably would say okay. But probably slightly left skewed. All right, what about this guy, the actresses? All these little dots right here, those are all outliers. So what do you think? Oh yeah, this is right skew. Now, when you see box plots that are sitting on one end, like this next one, you are going to need to make sure you're looking at it from lowest to highest. So usually if it's sitting on end, the lowest is this bottom part. So make sure you're looking at it from this way, lowest to highest. So what do you think? Right skew. Okay. All right, the last grouping here, I'm going to give you 30 seconds to label them. Ready, go. Time is up. All right, from left to right, tell me what you got. What's the first one? Approximately symmetric. I agree. Next. Left skew. Next. Right skew. Next. Approximately symmetric. Next. Left skew. All right. Any questions? Nice. All right, kids. Chapter 1. We are almost done with chapter 1. We have one more thing to talk about, and it is standard deviation. It is probably the most confusing thing of chapter 1. Yay! Aren't you glad we saved the best for last? But here's the good news. I think you're going to understand it fairly well, and you're going to be super happy when you find out you don't have to calculate it by hand. So that's going to be great. So here we go. If I told you guys that I get to school around 7 o'clock every morning, give or take 5 minutes, then about what time might I come to school? Any time from 6:55 to 7:05 would be correct. So on average, I'm getting here at 7 a.m. plus or minus 5 minutes. So that is somewhere between 6:55 a.m. to 7:05 a.m. If I got here any time within that time frame, it would be pretty average. It would be pretty normal for me. If I were getting here at 6:45 or 7:15, then that's kind of outside of my average, my normal, my typical time that I usually get here. So standard deviation is kind of like that give or take, so the 5 minutes that we're talking about here. we say that we have an average of something, and then we kind of give ourselves this little bit of this wiggle room because not everything is always exactly the same every time. So we kind of get this little bit of a wiggle room. That's standard deviation. That's what it really does measure. So standard deviation measures the typical variation from the mean. Standard deviation is the typical variation from the mean. It's basically an average of the distances each number is from the mean. It's an average distance that each number is from the mean. So if I had a distribution of 1, 2, 3, 4, 5, and what's the average of 1, 2, 3, 4, 5? 3. What's the distance from 3 to 1? It has a distance of 2. What's the distance from 3 to 2? 1. What's the distance from 3 to itself? 0. The distance from 3 to 4 is 1. The distance from 3 to 5 is 2. If I average all of those distances, so the average distance would be 2 plus 1 plus 1 plus 2. That's 2, 4, 6. 6 divided by 5. So that's 1.2. So there's an average distance of 1.2. So again, the average for the distribution is 3, but we have a little bit of wiggle room of what's considered, average or normal, which is 1.2. So it captures a majority of the data. It captures the 2 and the 4. The 1 and the 5 is a little outside of what would be normal, but they're not necessarily outliers unless you check the outlier rule. But that's kind of the idea behind standard deviation. It's the average distance from the mean out to every single data value and what that average distance is. So, with that being said, here's the formula. First, the notation. S sub x is how you say that. It's a little s with an x in the subscript. S sub x is how you say it. S sub x, standard deviation. I'm going to be honest with you guys. You'll probably see me write it 3-5 different ways. I might write standard dev like that, or I might write a capital SD. Any of those are actually pretty common, but S sub x is the official notation. And here's the formula. The super square root of the summation of x sub I minus x bar squared divided by n minus 1. Aren't you glad I've already told you don't have to do this by hand? Yeah. So what does this mean? All right. Obviously, square root. You guys know square root. Summation, we talked about already. That just means to add up things or to sum things up. X sub I, that means take each number in the distribution and subtract the mean and then square that value. So for that example we just had, I would do 1 minus 3 squared. Then I would do 2 minus 3 squared. And then 3 minus 3 squared, 4 minus 3 squared, 5 minus 3 squared. And then I would take all those squared numbers and I would add them up. I would take all the squared numbers and I would add them up. Then I would divide by n minus 1. N meaning the sample size number, or however many numbers there are. So in that previous example, 5 minus 1 is 4. So I would take that sum of all those distances and I would divide by 4. Then I would take the square root of that, and then I would have the standard deviation of 1.2, or whatever it actually is. That sounds fun, doesn't it? No, that sounds atrocious, you guys. We don't want to do that. We're going to use our calculator to do it. But I do want to take you through the process of how it works. So this is our SAT data. Here's what we would do. We would find the mean of this data, which we did find that last week. It was 1094. And then we would take each number and subtract the mean. So 900 minus 1094, and then we would square that. Then we'd go 900 minus 1094, and we would square that. And then 910 minus 1094, and we would square that. And so on and so forth and so forth and so forth. You can actually see that right down below. It says it right here. Take the number minus the mean squared. We get these numbers. So these are all the squared numbers. All the squared differences. We add all these up. Notice we started out getting negatives at first because those numbers were below the mean. But then we started getting positive because those numbers were above the mean. But we squared all of them. No more negatives because standard deviation is a distance from the mean. So we add all these guys up and we get 422,760. It's a big number. And then we divide by 15 minus 1 because there were 15 data values, so 14. We get 30,197. We take the square root of that. We get 173.77. So, on average, these kids had an average of 1094 for their SAT score. Give or take, plus or minus, 173.77. This is the plus or minus the standard deviation. So, what is considered an average score for this group of students? Well, if I take 1094 and I subtract 173.77, what would you get? 1094 minus 173.77? What is it? 920.23? Is that what you said? Yeah. Okay. So that would be like the low end of the average score for this group to the high end. Take 1094 and add 173.77. What's the high end? Perfect. This is now the average values that a student in this group might have gotten on the SAT. Are all of the numbers in that data set in between these? No. But this is the average distance that we might go from the mean. This is what would be considered an average score for someone in that group. If you're outside of that, it doesn't make you an outlier automatically, but it makes you a little suspicious. You're maybe a little above or below average. All good? Cool. Let's talk about standard deviation and whether or not you think it's resistant. Do you think standard deviation is resistant to extreme observation changes? Good. What do you guys think? Is standard deviation resistant? Heck no! Heck no! No! Standard deviation is based on a non-resistant mean. Standard deviation is based on a non-resistant mean. Also, standard deviation is an average distance. So it's like we're taking an average and basing it on an average. So we've got like two non-resistant things happening here. So standard deviation is very affected whenever you start changing numbers. All right, a couple of important things about standard deviation. First of all, standard deviation will always be greater than or equal to 0. Standard deviation will always be greater than or equal to 0. It's a distance. It has to be greater than or equal to 0. But how could it be 0? Good. S of x equals 0 if all values are the same. Here's an example. 5, 5, 5, 5, 5. What is the average of this data set? 5, 5, 5, 5, 5. No, what's the average of the data set? 5. The average is 5. Okay? If I add all those numbers up and divide by 5, I get 5. All right, so the average is 5. What's the distance from 5 to each of these numbers? That's 0. So the average distance is 0. There's no deviation from 5. 5 is the mean. There's no deviation from it. It's all the same. All right. And then finally, large spread. Large spreads equal large standard deviations. The bigger your spread is, the bigger your standard deviation is going to be, because your standard deviation has to factor in that big long distance from the mean. So the bigger your spread, the bigger your standard deviation is. All good? Everybody got all that? All right, cool. Let's look at these two graphs. Oh, wait, I'm sorry. Use our calculator. Sorry. We're going to use our calculator to find the standard deviation. I don't want you guys to do this by hand. I really don't. Nobody in the real world does standard deviation by hand. Like, why would I make you do it by hand? It's silly. So we're going to calculate the mean and standard deviation using our calculator. So you put your data into lists. So that's under stat edit. And then you're going to use your stat calc 1. This is your one variable stat. And your mean is going to be under X bar. And your standard deviation will be under, it says SX. The X is the same size as the S in your calculator, but that's where you're going to find standard deviation. So it's literally plugging the numbers into your calculator and telling your calculator to do some work. Otherwise, you're going to want to kill me because you don't want to do standard deviation by hand. Trust me. You don't. No fun. No bueno. Okay, now we can look at graphs. You guys ready to look at these graphs? All right, I need you guys to look at these graphs, and you and your group decide which one has a smaller standard deviation. The answer to the question you have all been waiting for. Which one has the smallest standard deviation? B.
Wrong answer.
Miss Lakey, how the heck is this true? Let me show you. So, would you guys agree that the average on both of these looks to be around 5-ish? Would you kind of agree that that's probably ish? Okay, sure. So here's the average, right? So, standard deviation is the distance from the mean. And so on B, I have to go out from 5 to 8 a few times, but look at how many times I have to go from 5 to 8 on graph A. And I have to average in that distance that many times. 10 times on the, or 11 times on this left side and like 8 times on the right side. That is a large distance that has to be averaged multiple times. It has to be included in the average multiple times. And so this has the smaller standard deviation because it doesn't have to go out as far as many times as this one does. Does that make sense? All right. I know you feel like I kind of tricked you, but I didn't, I promise. I did not. I would never. All right, let's look at this. A random sample of 5 students was asked how many minutes they spent doing homework the previous night. Here is their responses. 0 minutes, 25 minutes, 50 minutes, 60 minutes, or 90 minutes. We're going to calculate and interpret the mean and the standard deviation. Let's go to our calculator. Stat, edit. Stat, edit. Stat, edit. Everybody go to stat, edit. You're plugging in 0, 25, 50, 60, and 90. Please do not forget the 0. It is a part of the data set. 0, 25, 50, 60, and 90. Do you remember where to go? Next. Stat. Calc 1. Enter, enter, enter. And boom. 45 is the mean. Which one is the standard deviation? The SX 34.28.
Yes.
X bar is 45. S sub X 34.28. It does ask us to interpret. That means to write a sentence. The mean amount of time spent on homework was 45 minutes. This typically varies or varied by 34.28 minutes. So again, what would that mean? On average, 45 minutes plus or minus 34.28. So we're talking like 10.72 to 79.28 minutes, right? So like this is what would be considered average amount of time. So the person who did 0 and the person who did 90 are kind of outside of the average. But most of them were somewhere between 10.72 and 79.28. Any question about that? Last question of chapter 1. What would happen if we remove the 90-minute person? What would happen to the mean? Would it go up or down? It would go down. What would happen to the standard deviation if I take out that big distance? It would also go down. Both would decrease.